Alright, now time to solve some exponential and logarithmic equations. So we're definitely going to need those properties that we got in the previous chapter to apply them to logs in order to solve several different types of logarithmic versus exponential equations. So to begin, we will also need to think about what's called the one-to-one property of exponentials. So for any algebraic expressions, s and t, and any positive real number, b not equal to 0, b to the s equal to b to the t basically means that s equals t. So in other words, if we can get the same base in our problem, then we just can then look at the exponents themselves and set those equal to each other. So this is not always going to be possible, but certain problems will allow for this sort of manipulation. So here we have 3 to the 4x minus 6 is equal to 3 to the 2x over 9, and our goal is to solve for x. So right now, we do have a 3 and a 3, but this 9 sort of throws a wrench into it. So what can we do to help us here, to get that same base? Because essentially you really can't do much of anything with exponentials until they have the same base. And then we can start combining them and applying all of our exponent properties. Remember that. All those properties of exponents, properties of logs, only works when they have the same base. If they have different bases, can't really do any of them. So, well, luckily, 9 is 3 squared. So, if possible, your first step is going to be rewrite every base in the problem using the same base. So if you had 2 and 8 in the problem, you'd go 2 and then 2 cubed, etc. Just make sure all the same bases. If there was a 4, that's 2 squared. A 16, that's 2 to the 4th. You just rewrite all of the numbers in the same way, with the same base. So here we have 9 is 3 squared. Now, all of these things are just exponentials with a base of 3. But I can't apply the one-to-one property quite yet because it's not just one thing equal to another. There's still this division in there. But as I said at the end of the last chapter, we have a rule for exponentials that involves division. It's the quotient rule for exponents. Again, if you're rusty on your exponent rules, it's definitely something you're going to want to look into. So our exponent rule for division says that x to the b over x to the a is equal to x to the b minus a. So we take 3 to the 2x over 3 squared, and we just turn it into subtraction. So 3 to the 2x minus 2. Alright, so at this stage, we now actually have this property. We have base 3 on both sides, and so I can just get rid of those base 3's. Really what we're secretly doing is we're taking the log base 3 of both sides. Like that's what we're doing to cancel out those 3's. But we'll get into doing that a little bit later more visually. So for right now, we just take the exponents themselves. So 4x minus 6 equals 2x minus 2, and we set them equal to each other, and then we solve using our basic algebra techniques. 2x is going to be equal to 4, and then x equals 2. You should always check your answers in questions like this. For exponentials, there's not as much of a problem, but we will see later that if there's any logarithms involved, there's always the option that you might get what's called an extraneous solution. So you should be checking your answers anyway, but you should especially be checking your answers in this section. Okay, well, let's see some other examples of rewriting with the same base. So here we rewrote with the base 3. Here, I have 8 to the x plus 2 and 16 to the x plus 1. I want to rewrite these with the same base. But it's not as simple as just 16 is 8 squared, because that's not true. 8 squared is 64. So how are 8 and 16 related to each other? Well, I can change both of them to be the same base. Like I said before, 8 is 2 cubed and 16 is 2 to the 4th. So even if the 2 wasn't originally part of the problem, I can still bring it into the problem as long as they have that relationship. So I'm going to rewrite both of them. So 8 It's now 2 cubed to the x plus 2, and then 2 to the 4th to the x plus 1. And here's where another one of our exponent properties comes in. So x to the a to the b power is equal to x to the a times b. So here we have 2 to the 3rd to the x plus 2 means it's going to be 2 to the 3 times x plus 2, like so. Still up in our exponents. And 2 to the 4th to the x plus 1, of course, became 2 to the 4 times x plus 1, or 4x plus 4. And so now I have the same base. Both of them have 2, and it's simplified. Don't do it here. Don't simplify yet, or don't use that property yet, because they aren't to the same base yet. Here they are. Now I can get rid of my 2's and just have 3x plus 6 equals 4x plus 4, and I can solve from there. This slide is just about setting it same base, so I'm not going to go through the solving part, but again, once you have the same base, you apply that property, set the two exponents equal to each other, and solve using basic algebra methods. So let's look at the second example. So here we have 2 to the 5x equals square root of 2. This is another exponent property you're going to need to know, that the square root of 2 can be rewritten as 2 to the 1/2. So our property specifically is x is the a root of x to the b power, also written as the a root of x to the b power outside, is the same thing as x to the a over b. So in this case, a is 2 and b is 1. So x to the a over b, x to the b over a, wow. X to the b over a is equal to x to the 1/2. I apologize for that mistake. So x to the 1/2 power, or 2 to the 1/2 in this case because our x is 2. So we can rewrite this as 2 to the 5x equals 2 to the 1/2. So once we have that, we can then just say 5x equals 1/2 and go through solving by dividing by 5 and all of that. The next type of exponential or logarithmic equation problem we can run into is, well, when bases aren't so easily related. So in these previous problems, our bases had some sort of easy relation between them. They were both related to base 2, or they're all related to base 2, or they're all related to base 3 in the previous slide. So here, well, 5 and 4 don't have that nice sort of relation. 5 to any power is not going to be related to 4 to any power, and you can't take any roots of them that are going to be related in any way. So what can we do? Essentially, this is where taking a logarithm can really help us, and then we can apply our logarithm rules. So our first step when we see an exponential equal to another exponential, if there was other stuff going on, if this was like +2 or something like that, it gets a little bit tougher and we don't necessarily want to do this quite yet. But when it's just one exponential equal to another exponential, our first step is always going to be take a log. You have options for what log to take. It doesn't really matter. In general, I tend to take the natural log by default because it's just one that gets used in mathematics a lot, and so it's the one that I default to. You can even use the log base one of the bases that's given here. You can use log base 5 or log base 4. That'll allow for some extra simplification. But I'm going to work with the natural log as, again, that is sort of the one that we default to. So once I have the natural log of both sides, so again, these are just fully inside of our natural log now, I can apply all of those log properties that I used in the previous chapter. So we can see, well, these are exponentials, so they have exponents. And I have my power rule of logs. So remember, the power rule of logs is log base b of m to the n power is equal to n times log base b of m. So we're going to apply this property. We're going to bring those exponents up front to get x plus 2 times ln of 5 is equal to x times ln of 4. Then we can even split this up further. We're going to distribute the x plus 2 to get x times ln 5 plus 2 ln 5 equals x ln 4. Next step is going to be to isolate our x. We're just trying to move our x's, anything with x, all to the same side. So this is going to move over here, and we're going to move the one that doesn't have an x to be alone on the other side. So that's x ln 5 minus x ln 4 is equal to negative 2 ln 5. And our final couple steps are just going to be bring that x out, factor it out like this, and divide, like so. And divide, so we get x is equal to negative 2 ln 5 over ln 5 minus ln 4. All of this is ugly, obviously, but it is something that we can evaluate. We can plug this into a calculator and figure out what number it is. Again, it's not necessarily pretty, but it's certainly something we can do. Alternatively, the way I have actually written here is to do some simplification before we get to that step. It's not necessary, but it does make plugging it into the calculator easier if we do this simplification. So ln 5 minus ln 4, well, we've got a minus, we have the same base on our logs, so we can condense now. So we did some expansion first back here, and now we're going to do some condensing. So ln 5 minus ln 4 becomes ln of 5 over 4. And similarly, that negative 2 can be brought inside to be ln of 5 to the negative 2 power. Now notice I did write this as 1/25, but this is 5 to the negative 2 power, because remember that would be 1 over 5 squared, which is 1/25. So once we're there, we now divide over ln of 5/4, and we can solve for x. Again, this means the same thing as what I had previously written, but it's a little bit easier on the eyes. It's also a little bit easier to write in your calculator and not make a mistake. So you have options for your answer. This is just the nicer, more preferred way of doing it. All right, what about equations containing e? Because like I said, e tends to be our default, or ln tends to be our default. That can really help us when we're dealing with an equation that contains e itself. And we're certainly going to see stuff containing e in the next chapter. E is very important when it comes to natural problems. So we need to know how to solve an equation containing e. So for example, if we have 94 equal to 20 to the power of 2t minus 6, and we're trying to solve for t, we first apply basic algebra by adding 6 and then dividing by 20. So I add 6, I divide by 20, so I get 5 equals e to the 2t. I'm isolating my e here. If it wasn't e, if it was any other base, I would still do it the same way. If this was base 3 or base 7 or anything else, I would do the same things, because I try to isolate my exponent to get it to just be one exponential without any addition or anything going on. So once I've isolated this e to the power, I can then use my logarithm, my natural logarithm on both sides. So I'm going to take ln of 5, ln of e to the 2t, but remember, well, ln of e to the 2t, that's technically saying log base e of e to the 2t. When we have the same base, they cancel out, and so we get just ln of 5 equals 2t. Once we're here, divide by 2 and we're done. So t equals ln of 5 divided by 2. And again, we will certainly be seeing real-world examples where we're going to have to be able to apply these properties in the next chapter. But there is a sort of weirder example that we can run into. So this is e to the 2x minus e to the x equals 56. So, well, what's going on here exactly? This one is a little bit trickier, and your first thought may be, okay, well, there's subtraction, and can I turn that into division? No, because remember, our exponent property is x to the a divided by x to the b equals x to the a minus b, not x to the a minus x to the b equals the division. That's the logarithm property, so don't get them confused. So I can't apply this to this question. So instead what I'm going to do is I'm going to move that 56 over. E to the 2x and e to the x cannot be combined. They do not become e to the 3x, and they do not become e to the 1x when you subtract. They don't combine. It's the same thing as saying x squared minus x. Oh, that's a little bit interesting, though, that I bring that up. Well, essentially, what I can do is I really can think of this as x squared, because what's really happening here is e to the 2x using one of our log properties, x to the a to the b power is equal to x to the a times b. Well, this is 2 times x, so that means this is like e to the x squared, right? So I have e to the x squared minus e to the x minus 56 equals 0. So that's something squared minus itself minus 56. So maybe I can use some things I know about when I have a square, and then the not square version, the first power version, and then a constant. That's looking very similar to our x squared minus x minus 56, right? Let's call it, instead of x, I'm just going to use a different letter real quick. So what if instead I said this was, let's go with w squared minus w equals, minus 56 equals 0. And then I can say, well, w just equals e to the x. So now this equation and this equation are the same thing. If w is e to the x, then those two equations are equivalent, right? And this is something I know how to solve. This would be w minus 8 times w minus 7 equals 0, right? So what does that mean for e to the x? Well, that means it's e to the x minus 8, e to the x minus 7. And so I can actually factor, or e to the x plus 7, I should say, I apologize, that is a plus. So I can factor this into e to the x plus 7 times e to the x minus 8 equals 0. So we factor, when we have e to the 2x, e to the x together in the same problem, we factor it. And then we solve. So e to the x plus 7 equals 0, e to the x minus 8 equals 0. We go through and solve. But there's one problem, and like I said before, extraneous solutions. An extraneous solution means we're getting an answer that doesn't actually exist. We've done everything right, but just due to the nature of how we solve the problem, there might be a little discrepancy. There might be something wrong. Doesn't mean you did anything wrong, it's just that you always have to remember to check your answers, plug them back in, make sure they make sense. E to the x can never equal 7 because, well, or it can never equal negative 7 because the range of an exponential is 0 to infinity. It's never going to be equal to negative 7. And the way we would actually solve this would be to take the natural log of both sides, and I can't take the natural log of negative 7. So that answer just doesn't exist. So we ignore this one entirely. This is just an extraneous solution, and our final answer is x equals ln of 8. Again, by taking the natural log of both sides of e to the x equal to 8. Finally, we are now going to look at using the definition of a logarithm to help us solve an equation. So, for any algebraic expression S, and real numbers b and c, where, once again, as always, b is greater than 0, b is not equal to 1, we get log base b of s equals c if and only if b to the c equals s. It's the same thing as the definition of log. We're using this. I've changed the letters just to sort of make sure you're paying attention. But again, we're now going to use this where s is a whole expression instead of just some number. So for example, if I have 2 ln of x plus 1 equal to 10, well, first step for solving an equation like this is to isolate the log, because I can't use this property until there's nothing in front of my log, until there's nothing else happening, until it's just log base something of something equals something. So I'm going to get rid of this 2. Technically I have two options. I could bring it inside, or I could just divide it out. We're going to divide it out, because that's going to be nicer. So ln of x plus 1 equals 5. Then, next, I'm going to take this and apply this property. So I'm going to trade places. The x plus 1 and the 5. Remember that our base is e, so we get e to the 5th power equals x plus 1. So that's using this property. That's flip-flopping the two, using the fact that they are inverses of each other to just rewrite my problem. Really what I'm doing is I'm just taking e to the power of both sides, because that causes this sort of cancellation. So then, well, e to the 5th power is just a number, so when I solve x equals e to the 5th minus 1, it's just a number. E to the 5th, once again, it's not something I can do in my head. It's 2.718 to the 5th power, whatever number that would be, minus 1. So I'm going to leave it in its unsimplified form here, and that's okay, unless you are specifically asked, like in a word problem, to find the actual numerical answer to say like a number of feet or a time or whatever. You can leave it as e to the 5th minus 1. I don't need the decimal approximation. Now, using this, we can also apply the one-to-one property for logs to solve similar types of equations. So here we have there's one log in our problem. But if there are two logs in our problem, things get more complicated. So, just like with the exponential, we can say that log base b of s equal to log base b of t just means that s equals t. Again, they have to have the same base to use this property. So, note, when solving an equation involving logs, always check to see if the answer is correct or if it's extraneous. This is where you're definitely going to run into extraneous solutions. Extraneous, once again, just meaning that you did everything correctly, but due to the nature of logarithms, something happened that causes that answer to not actually work the way you want it to. So you have to check, is this answer actually actually allowed to be plugged into a log? Or am I outside of the domain? So you want to check within your domain. So here we have ln of x squared minus 2 equals ln of x. So these are a log equal to a log where they have the same base, that base e. So I can just immediately ignore them. I just cancel them out, essentially, and so I'm getting x squared minus 2 equals x. And now this is something hopefully we all know how to solve. We move the x over and set it equal to 0, and then we can factor it. So this is a pretty simple quadratic factoring into x minus 2 times x plus 1. And so we get x equals 2 and x equals negative 1. But where things get more difficult is, once again, remember to plug back in. We have to plug into both of them. If there's more than one log in your problem, you have to check the domain of each one of them individually. So, or you can just state your domain at the beginning. So here, the domain of ln of x squared minus 2, well, x squared is always positive. We're moving it over 2. The domain of this one is actually just, open parenthesis, 2 to infinity. The domain of this one is 0 to infinity. So, square root of 2 to infinity, my bad. So, well, 2 is luckily greater than both of those, but negative 1 is not. ln of negative 1 doesn't exist. Similarly, ln of negative 1 squared, which is 1 minus 2, would be negative 1, so that'd be ln of negative 1 as well. So yeah, you'd get ln of negative 1 equal to ln of negative 1, which is lovely, but doesn't matter because they don't exist. They are not within the domain, so it doesn't matter that it works out that way. So x equal to negative 1 is extraneous, and so if you left your answer like this, if this was your full answer, you would get marked wrong. Yes, most of your work is correct, and you'd get credit for that, but you would not get the final answer correct. You have to note when there is an extraneous solution. Now let's look at a brief application example. Again, the next chapter is all about application examples, but just to apply some of the properties that we've learned here, we have the percentage of adult height attained by a girl who is x years old can be modeled by the function f of x equal to 62 plus 35 log, common log specifically, of x minus 4, where x represents the girl's age from 5 to 15 and f of x represents the percentage of her adult height. At what age has a girl attained 97% of her adult height? So, essentially, let's highlight what's important here. What are we looking for? We're looking for the percentage of her adult height. we have a function that gives the percentage of her adult height, and we're specifically looking for when it's 97%. So, in other words, we're asking, well, when is f of x equal to 97? And you may be saying, well, shouldn't it be 0.97? And specifically, it is 97 because we're told f of x represents the percentage, so f of x is the whole number version, not the decimal version. So when does f of x equal 97? All right, so we take our function, we set it equal to 97. Easy enough. But what do we do from there? Remember that I said, no matter what type of logarithm we're working with, you always want to isolate it. If there's only one of them, that's what you want to do. Is isolate your logs. Same way with exponentials. You isolate your exponentials. So we are going to subtract off that 62 and then divide by 35, which is really nice because we got 35 on the left. And when we divide by 35, it just is 1 equals log x plus 4. So again, this is the common log, so remember, common log means log of x equals y translates into 10 to the y equals x, right? These are the same thing. So we are going to use that property to rewrite this as 10 to the first power equals x minus 4, equals x plus 4. My mistake. So then we're going to get... we are going to add, oh wow, actually, these are supposed to be the minuses. That's my bad. I am so sorry for that. I don't know what happened on those. So equals x minus 4 from the original. Okay, so from there, we are going to add 4. So once we add 4, we get x equals 14 in the end. Looks like I fixed the minuses on this slide. It was just that one bad slide. I'm so sorry. So since x equals 14 is not extraneous, because remember, we want to plug that in. So 14 minus 4 is 10. Log of 10 is totally fine. A girl has attained 97% of her adult height at approximately age 14 by this equation. So that's how we can see some generally application examples. You'll be provided an equation if it's going to be something tricky like this. But our next chapter is going to be all about figuring out those equations based on common types of equations that we'll see. And then applying all of these properties.